Hello viewers, welcome to add-on. In this question, we are asked to explain the VI characteristics of C configuration. It means we are asked about the input and output characteristics of C configuration. Okay, so let us start with the C configuration. Okay, so we know that a transistor has three terminals, which are emitter, base, and collector, where the emitter is highly doped, base is lightly doped, and the collector is moderately doped. I am denoting the doping level by using this plus signal. This is 4 plus, which signifies that it is highly doped. This is a single plus, which signifies this is slightly doped. And these are 2 plus, which signifies the collector is moderately doped. So let us draw the C configuration first. So if I am assuming a NPN transistor, so this is the collector terminal, this is the base terminal, this is the emitter terminal. Okay. So this is N, this is P, this is N again. So in the CE mode, the CE mode means common emitter. Means the emitter terminal is common to both the input and output. Also, in other words, it signifies that the emitter terminal is connected to the ground. Okay. So we are connecting the emitter terminal to the ground here. Okay. And we are applying the input at the base. Okay. So at the base, we are applying the input and across this collector terminal, we are taking the output. Okay. So as we can see, the emitter terminal, this is common to both the input section as well as the output section. So this mode is known for common emitter configuration. Okay. So this is just the normal representation. If we draw the circuit diagram, it will be like this. Okay. So this is the emitter terminal, which is connected to the ground. So the current flowing through it is I of C, emitter current. This is the input which we are applying across the base and emitter terminal. So through the base current IB is flowing, and this is the collector terminal, okay, through which the collector current is flowing, and this is the collector resistance across which we are taking the output here, okay. So the input is applied between the base terminal and the emitter terminal. Okay. So the input voltage will be denoted as plus minus V of BE. And in the output section, the output is taken within the collector terminal and the emitter terminal. So the output voltage will be denoted as V of CE. Okay. So this is the voltage between base and emitter, and this is the voltage between the collector and emitter. Okay. So the input voltage V of BE is applied between the base and the emitter terminal, and the output voltage V of CE is applied between emitter and the collector terminal. And the output current here, which is IC, is taken across emitter and collector terminal as well. Okay. So we know the base emitter junction, this is forward biased. Okay. So the input side is forward biased and the collector base terminal, this is reverse biased. So the output side is reverse biased. Okay. This is forward biased and this is reverse biased. Okay. So what happens during forward bias? The electrons from the emitter goes to the base, and within the base, there are holes present as it is p-type. But as the base is lightly doped, a few number of electrons will recombine with the base, which will generate the recombination current, and the remaining of electrons will flow to the collector. So this emitter current is responsible for the base current as well as collector current. But the value of base current, as I have said, is very low because only few electrons combine with few number of holes. So if we consider the emitter current like 5 milliamps and the collector current like 4 milliamps, IB will almost like some microamps. Okay. This is very low, right? So if the emitter and collector current are in milliamps, then IB will be in microamps. Okay. So here in this case, the input and the output impedance are moderate in common emitter configuration because this is the base current, right? So this is the base current. As we know, the base current is very low. So as the base current is low, it signifies the input impedance is high. Okay. As the input impedance is high, the base current is low. Okay. And in the output section as well, that this is the collector current. This have a moderate value. So in the C configuration, the input and the output impedance have a moderate value. So the current and the voltage gain both have a moderate value. They are neither extremely too high or nor extremely too low. Okay. So C amplifier, C transistor configuration provide us with suitable amplification. So this is the most widely used amplification, or we can say transistor configuration. So at first, let us describe its input characteristics. So the input characteristics is the plot between the input voltage and the input current. The input voltage is V of B, the input current is IB. Okay. So this is the plot between the input current and the input voltage. We are taking the input current, which is IB, in the range of microamperes along y-axis, and we are taking the input voltage V of B, which is in volt, along the x-axis. And this plot is taken or is made by taking the output voltage as a parameter. The output voltage is V of C. So it is taken as a parameter. Okay. So what happens is, when we are increasing the base emitter voltage, what happens? The potential barrier between the emitter and the base junction is gradually reduced. So as the potential barrier is gradually reduced, more number of electrons will go to the base terminal from the emitter terminal, right? So as more number of electrons go to the base terminal from the emitter terminal, the rate of recombination will increase. Okay. So as we are increasing the value of base emitter voltage, the base current will gradually increase. Okay. Because the recombination current will gradually increase. Okay. And suppose this is the curve for V of C, which is the output voltage at 0 volt. We haven't applied any collector emitter voltage. Okay. Now we want to see that if we vary this parameter V of C, or if we fix the value of V of C at some certain value like 10 volt or 5 volt, what will happen to the curve? Okay. So during this time, what happens? The output voltage V of C is kept at 0. Okay. And the input voltage V of B is gradually increased, and the input current IB is noted, which we have done in this case. So secondly, the output voltage V of C is increased like 10 volt, 20 volt, and they will be kept constant like this as well. And we will note the value of IB. Okay. So what happens here is, when the value of VB is increased, initially there is no current. Okay. But when the value of VBE reached a certain value, the value of IB will increase. Okay. And when the output voltage is increased, the curve will shift to the right hand side, which signifies what? If the value of VC is increased, suppose this is the value of VC at 10 volt, and this is the value of VC at 20 volt. So this is the curve corresponding to VC at 20 volt. This is the curve corresponding to VC at 10 volt. And this is the curve corresponding to VC at 0 volt. One thing we can see from this curve is that as the value of VC is gradually increasing, the curve is shifting towards the right hand side. Okay. So what does this signifies? Suppose we are considering a particular point at the value of VB. So suppose at this point, for value of VC, the value of base current is at this point. Similarly, at this point, when the value of VC was less than this value, this was 20 volt. So at that point, base current is at this particular value. But at 10 volt, the base current is at this value. Similarly, at 0 volt, the base current at this value. So as we can see, as we are increasing the collector emitter voltage, the value of base current is gradually falling. Why does this happens? We know the collector base junction, this is reverse passed. Okay. So when the collector emitter junction voltage, when this voltage is gradually increased, what happens is that the collector terminal becomes more positive. Okay. As we are increasing the collector emitter voltage, the collector terminal becomes more positive. So the reverse bias of collector base terminal will gradually increase. And as the reverse bias gradually increase, the width of the depletion region will gradually increase too. Okay. So due to this reason, the base current will gradually fall. Okay. Because this collector emitter terminal, this is the voltage between the collector terminal and the emitter terminal. Okay. So when we are increasing this value of the collector emitter terminal, suppose V of C, this is plus, this is minus. So when this voltage is increased, this value of plus is gradually increasing and this value of minus is gradually decreasing. So as we know, the base emitter junction was forward bias, which was responsible for the flow of electrons from emitter to the base. Now, as we increasing the collector emitter voltage, the value of voltage at the emitter terminal is decreasing. So what happens is that this forward bias will gradually decrease. So if the forward bias is gradually decreased, electrons will not pass from the emitter to the base. As the electrons won't pass to the emitter to the base, the recombination won't occur. The rate of recombination won't be that much high. Here we can see when the collector emitter voltage was 0, the rate of recombination was very high. But as we are applying it, the value of emitter voltage is gradually decreasing. So the base emitter junction forward bias is gradually decreasing. So the electrons are unable to go from the emitter to the base. So the recombination rate or the recombination current is gradually falling. So here we can see the base current is gradually falling. Okay. So this is the input output characteristics. Similarly, in the output characteristics, we will be plotting the output voltage. The output voltage was V of CE against the output current, which was IC, keeping the parameter IB. Okay. So the output voltage and output current are plotted and the input current will be the parameter. So the curve will be somewhat like this. At first, let us draw a straight line here. So the curve will be like this. This will be a straight line here. It won't vary. Okay. So the y-axis is the output current, which is the collector current in the range of milliamps. This is the output voltage along x-axis, which is V of CE volt, and these are all the base current. IB is equal to 0 microamps. IB is equal to 10 microamps. And similarly, it is 20 microamps and it is 30 microamps. Okay. So the output current is plotted against the output voltage. Okay. Keeping the input current as a parameter. Okay. So one thing we can see that at first, when the value of VCE is at 0, the value of collector current is 0. And as the value of VCE, this voltage is increased, the collector current is increasing, but at a particular point, the value is saturating. Okay. So this region where the value is saturating, this is the active region. This region where the value of IC is 0, this is value of IB is 0, this is the cutoff region, and this region is the saturation region. Okay. So in the active region, when the output voltage is increased, there is a slight change in the very slight change in the output voltage. Okay. Because in the active region, we can see this is the active region. When the output voltage is changed, the value of output current is almost the same. It is almost the same, and we can say it is not varying at all. Okay. And the cutoff region is the region where the input current is below. This is the region. This is the cutoff region where the input current IB is 0, or we can say this is the region below the input current is equal to 0 microamps. Okay, or we can say it is a particular point where the value of the collector current is 0 milliamps, sorry. And when both the junction are forward biased, this is the saturation region. Okay. Now let us explain why does this scenario happens. So at first, we know the emitter current is equals to base current plus collector current. Okay. So this is the value of VC, which is the voltage between the collector terminal and the emitter terminal. So when the value of the voltage at the collector terminal and the emitter terminal is increased, at that particular point, the value of the collector current will increase. Okay. The value of the collector current will increase, but after reaching a particular value, a certain value, the value of the collector current won't increase as much. It will become constant. Okay. And after that, if we increase the value of the parameter, which is IB in our case, if we increase the value of the IB, we can see the value of the collector current is increased, because at first this IB was 0. So all the collector current, this is the collector current, right? So this collector current is not at all influenced by this base current. Okay. But when the value of the base current is increasing, which signifies what? This signifies that the electrons, more and more electrons are flowing from the emitter terminal to the base terminal, for which recombination is occurring. And as the recombination occurring, recombination current is generating, which is the base current. And the more the number of the electrons are passing to the emitter to the base, the more the number of the electrons will be passed on to the collector terminal. So the flow of the current in the collector terminal, which is IC, will be increasing. So as we are increasing the value of IB, the value of IC will gradually increase too. So this is all for the VI characteristics of C configuration. Thank you.